This is the Chapter 6 quiz, Chemistry 101, Spring 2021. Pressure. For conversion, we're asked for what the pressure is in ATM, starting out in millimeters of mercury. 1 ATM, 760 millimeters of mercury. We have 128 millimeters of mercury. We have an equality. We can create, excuse me, we can create two fractional friends. 760 millimeters of mercury on the bottom, 1 ATM on the top. 760 cancels out, lefting with units of ATM. Answer here is 0.168. Same kind of problem, number 2. We are going from PSI, and ultimately we want to end up in millimeters of mercury. But there are no conversion units to go directly from PSI directly to millimeters of mercury. You need to go through ATM. So you convert PSI to ATM, then ATM to millimeters of mercury. So there are 14.7 PSI for 1 ATM. We are at 2,350 PSI over 1 ATM, 760 millimeters of mercury. So it's 2,350 divided by 14.7 times 760. Our answer here is 1.21 times 10 to the 5th millimeters of mercury. Number 3. Sample of gas is at 115 degrees Kelvin, heated to 345 at constant pressure. What volume does the gas occupy now? This kind of problem. 3 laws. Pivnert, PV equals nRT. Combined, P1, V1, T1, P2, V2, T2, Dalton's, P total is equal to partial pressure of 1 plus 2, 3, whatever. See if I can find a different marker that you can read. So, what are we given? Pp equals nRT. N is the number of moles. Do we have any information about moles in this problem? No. The only thing we have are pressure and temperature. Since this deals with numbers of moles, we cannot use that. Dalton's law says we're dealing with only pressure. Do we have pressure here? No. It says it's constant pressure. So the pressure doesn't change. The only thing we have left is the combined gas law. If pressure is constant, we have V1 over T1 is equal to V2 over T2. It's asking what is the volume of the new, what volume does the gas occupy after it's been heated? So we're looking for V2. We solve by multiplying both sides by T2 over 1. Whatever we do to one side, we need to do to the other. T2 on the bottom drops out, T2 on the top, so we have T2, V1, T1 is equal to V2. T2 is 345 K. V1 is 54.2. T1 is 115 K. So temperature units are in the right units in all gas problems. If you have temperature and you're using it as a value, you must be in units of Kelvin. 345 times 54.2 divided by 115, the answer comes out to be 163 liters, number D. Number 4, what is the temperature of 1 liter of a gas? That is at 30 degrees C and 1.75 ATM. It's changed to 25. What's the final pressure of the system at constant volume? Again, Pivnert, PV equals nRT. V1, T1, excuse me, P1, V1 over T1 is equal to P2 V2 over T2. And Dalton's law. P total, P1 plus P2 plus P3 plus however many other partial pressures of the component mixture of your gases. Do we have more than one gas? No. This is a gas sample, one sample. Do we have any components to it? No. So we have no information about multiple components. Not Dalton's. PV equals nRT. That deals with pressure, volume, number of moles, and temperature. Do we have any information about moles here? No. You cannot use PV equals nRT. You're left with P1 V1 over T1 is equal to P2 V2 over T2. What is the final pressure? We're looking at P2, constant volume. It means V2 and V1 are the same. The pressure, the volume doesn't change. So you're looking for P1 over T1 is equal to P2 over T2. To get P2 by itself, multiply both sides by T2 over 1. T2's cancel, so we're left with T2. P1 over T1 is equal to P2. T2 here is 225. We need to convert that to Kelvin. Remember, gas calculations, temperature must be done in temperature Kelvin. Convert Celsius to Kelvin by adding 273, 225, 273, 8, 9, 4. So T2 is 498 Kelvin. P1 is 1.75 ATM. T1 is 30 degrees C. We need to convert that to Kelvin. So 273 plus 30, 3, so that's 303. So it's 498 times 1.75 divided by 3.3. The answer numerically is not provided amongst all these. So the correct answer here is E, none of the above. Number 5. Weather balloon contains 233 liters of helium at 22 degrees C at 760 millimeters of mercury. What's the volume of the balloon when it ascends to an altitude where the temperature is minus 54 and the pressure is 511 millimeters of mercury? Do we have moles? Weather balloon contains 233 liters of helium, 22 degrees 760 volume, pressure, volume of the balloon. So we don't have moles there, so we can't use Pivnert. Second gas law, Dalton's law. Do we have information about just pressure alone? No. It asks, what's the volume of the balloon? So we don't use Dalton's. The only thing left is combine. P1, V1, T1, P2, V2, T2. What is the volume of the balloon? V2. When it ascends to an altitude where the temperature is minus 54 and the pressure is 511 millimeters of mercury. We need to get V2 by itself. We do that by multiplying both sides by T2 over P2. T2's drop out, P2's drop out. We're left with V2. So it's T2 times P1 V1 divided by P2 T1. So T2 here is minus 54 degrees C. That must be in Kelvin. So 273 minus 54. 19. So T2 is 219. P1 is 760. V1 is 233. P2 is 511. T1 is 22 degrees C. We need to change that to Kelvin, so 273. 22 is 295. So we've got 219 times 760 times 233 divided by 511 and 295. Your answer here should be D, 257 liters. Number 6. What is the volume of 62.3 grams of nitrogen gas at STP? Again, do we have information about moles? Not directly. That's just volume. Do we have a change in conditions of temperature, pressure, and volume. Well, STP, excuse me, is T for STP is 273 Kelvin. P is 1 atm. So we only have one temperature and one pressure. And asks what the volume is. So we can't use Dalton's law because that deals with only pressure. We've got temperature and pressure. What about combined gas law? Do we have two sets of temperature, pressures, or volume? No, we don't. It asks for volume given grams. The only equation we have left is the ideal gas law, PV equals nRT. Solve for volume, we divide both sides by P. V equals nRT divided by P. And here is the number of moles. Well, do we have numbers of moles? No, we have grams. But if we walk that grams to moles, we can get an answer. So 62.3 grams of N2 over 1. Avogadro said the gram mass weight of all the elements present is equal to 1 mole. So we have N2 is a molecular formula. 1 mole of N2 has 2 moles of nitrogen. 1 mole of nitrogen is equal to 14 grams. The gram mass weight of the element nitrogen exactly as it is off the periodic table. So 1 would be 14, 2 would be 28. 28 grams N2, 1 mole N2. So we take 62.3 divided by 28. That's the number of moles. We plug that moles into our equation. R is 0.0821. Temperature is, 273 K. Pressure is 1 atm. Plug in the number of moles that we get here. Calculation should give you 49.8. Answer C. Number 7, how many moles of gas are contained in 5.33 liters of O2 at conditions of STP? Okay, again, since now we have moles, it's asking us for the value of N. We have liters, 5.33. We have at standard conditions of temperature and pressure. Temperature is 273 Kelvin, pressure is 1 atm. So we need to solve for N. Divide both sides by RT. So PV over RT is equal to N. Pressure is 1 atm. Volume is 5.33. R is 0.0821. Temperature is 273 Kelvin. So it's 1 times 5.33 divided by 0.0821 divided by 273. Here, the answer should be A, 0.238 moles of O2. Number 8, what volume does 7.50 times 10 to the 20th molecules occupy at STP? Looking at moles of O2 gas. So we're looking volume PV equals nRT. So do we know pressure? Yes, 1 atm. Temperature? Yes, 273. R, we know, 0.0821. It's asking for volume. Avogadro said that 1 mole of any compound has 6.022 times 10 to the 23rd molecules. So we need, if it's asking for volume, we need to get volume by itself. Divide both sides by pressure. Volume equals N RT over pressure. Pressure is 1 atm. Temperature, 273. R, 0.0821. And number of moles. Avogadro said 1 mole of any compound is 6.022 times 10 to the 23rd molecules is 1 mole. Well, do we have 6.022 times 10 to the 23rd? No, we've got 7.50 times 10 to the 20th molecules. So we have 7.50 times 10 to the 20th molecules, O2, 1 mole O2, 6.022 times 10 to the 23rd molecules O2. Get that number of moles, 7.50 times 10 to the 20th divided by 6.022 times 10 to the 23rd. That's our number of moles. Plug that number of moles in right there. Allows you to calculate your volume. Should be B, 0.0279 liters. Number 9. Sample of gas contains 4 gases following partial pressures: helium, neon, argon, and xenon. What's the total pressure of the system? What information do we have? We have only pressures. What gas law that I've shown to you deals with situations where you have a mixture of gases and only information about pressures. P total is equal to the partial pressure of each of the component gases. Here we have 4 components: helium, neon, argon, and xenon. The total pressure is equal to the partial pressure of helium, neon, argon, and xenon. So helium is 113, neon is 184, argon is 35, plus xenon is 445. So 445 plus 35 plus 184 plus 113 comes to 777 millimeters of mercury. Answer A. Finding number 10. Sample of gas contains 4 gases: helium, neon, argon, neon. Helium, neon, argon, and xenon, excuse me. The following partial pressures: helium is 43 millimeters of mercury, argon 835, xenon is 111. Total pressure of container is 1355. What's the partial pressure of neon? Dalton's law again. P total is equal to the partial pressure of helium plus the partial pressure of argon plus the partial pressure of xenon helium, argon, xenon, and neon. What's the partial pressure of neon? So we have our P total, 1355. Helium is 43. Argon is 835. Xenon is 111. So it's 135 minus 43 minus 835 minus 111. Answer should be B, 366 millimeters of mercury. This is the Chapter 6 quiz. If you have any questions, if this doesn't answer you, or I've made a mistake, please talk to me in person and we'll get this worked out. Thank you very much. Have a good day.